Hydrostatics falls into a subset of engineering problems called statics. So we're going to learn a little bit of an introduction here about how to play by the rules of statics, many of which you already have, I think, within problem solving. We review here Newton's laws. Every object continues in a state of rest or in a uniform motion in a straight line unless it is compelled to change that state by forces impressed upon it. More or less inertia. F equals ma, force equals mass times acceleration. The change in motion is proportional to the motive force impressed and is made in the direction of the right straight line in which that force is impressed. In other words, you accelerate in the direction of the force. You've seen that already with regard to projectile motion, where the acceleration is down because that is the force of gravity. For a reaction, there is an equal and an opposite reaction. This is also written sometimes as the sum of the forces equals the change in momentum over time. For every action, there is always opposed and equal reaction. Or if two bodies are acting on each other, the actions are equal and opposite. Again, these are written, actually, I believe, in Newton's actual words. So the key thing here is that when you're breaking up a body into two forces, when you're doing free body diagrams, not in terms of one sum of one whole thing, but you are actually breaking up a free body into sub-pieces. When you cut them, there's equal and opposite forces at the cut. We've looked at the conservation of mass. You'll see that comes in quite importantly when you get into Bernoulli's equation. Conservation of energy, which will be, in fact, the main force behind Bernoulli's equation. For us up to now, it has been mostly potential and kinetic energy, with the potential energy being the potential energy due to position, and the kinetic energy being the kinetic energy due to translation, though we know there are more energies than that we must deal with. Rotation and spring energy already we've covered. From F equals ma comes the law of linear momentum. An interesting subset of the linear momentum rule is the fact that if you have an explosion, that the center of mass of all those objects in the explosion continues to act in the way that the piece did prior to its explosion, either standing still or flying in a projectile. Hopefully by now, in many, many different ways, but most recently in the engineering notation of I, J, and K, you know how to add and subtract vectors. You subtract by adding the negative, or the back azimuth, if you would, of the other vector. You know how to multiply or divide a vector by a scalar not having direction, and you know how to multiply two vectors and either as a dot product or as a cross product. And we will look at how we do that graphically, but mostly we will be relying on matrix algebra, which will then be put into the calculators. And then know that I, J, and K are unit vectors in the x, y, and z directions as defined by you when you define a coordinate system, and that the lambda unit vector is a unit vector in the direction of the vector you are talking about. It is then multiplied by a scalar being the magnitude. Remember that I, J, and K, as well as lambda, are the thing or the sub-piece of a vector which carries the direction in the units. This will become pretty clear, and we're going to cover this in hydrostatics so that we can learn to visually solve problems. One is the rule of transmissibility, that when you have a resultant or a force acting on a body, it can be moved along its line of action without changing the dynamics or the statics of the problem. We would like to do this so that when we're visually solving the problem, we can see to where actually the radial vector acts. So what we'll be doing is, if we have something pushing on something typically water or hydrostatic force, we will slide the vector so that its tail is at the point of application. You've already learned to do this in physics, and this is Varignon's rule. This is the rule that says you can break up a vector into components, and the actions of each of those components will be the same as that sum vector. Remember that the moment is the cross product of the radial vector and the force vector. Going back to what we did the first couple of weeks, we know that the angular velocity is the cross product of the radial vector and the velocity vector. And get in our heads early and often that the rule of statics apply. For them to apply, you both have to do the sum of forces and the sum of moments, and you will see that sum of moments can be about any arbitrary point in the system. There's your review, and we'll cover pieces of this again in the next couple weeks with hydrostatics. It comes back over and over and over again, as you've already seen within engineering. And finally, you'll see that moments can be defined in a number of ways. We want to right now get to the point where we know it is actually the cross product of the radial vector and the force vector.